Welcome again, everybody. My name is Kosseila, aka Clouddude. That's mostly in the Slack. That's my ID. As you've heard, we'll have a very interesting talk today. Two talks. One around P2p caching from Mao, and a new NP mode design from Yihua.
Oh, I'm sorry. That second topic is coming next month.
Oh, okay. My bad.
MP,
My bad.
that's
All
okay.
right. So we'll be having one, but that's a sneak peek on the next one. So that's good. You heard it here. So to kick things off, just a quick primer on the LMCache project for those who aren't familiar. I'd like to share a few words about the project. So so LMCache is the fastest growing AI and LLM memory caching project that makes inference incredibly fast and efficient. It's already shipped by default in popular inference engines like vllm, along with SGLang, and it helps QB cache offloading to many backends, being CPU RAM, local storage, or even remote storage backends like S3 or Redis through API connectors. You can see the impressive growth since the last few months. We now reach more than 7,600 stars on GitHub, which is really amazing. And I would like to share some recent updates and progress on the projects these last 2 weeks. Most of them would be a new release. So let's get to it. There you go. So this is a brand new release. So we went from 0.3.15 to 0.4 like 2 days ago. So that's pretty recent. And first, you got to notice that with this 0.4 release, it's just another evidence that we're introducing a focus on multi-process connectors. And I'll just explain a little bit what the team and maintainers have been busy doing recently, but this is covering more or less the whole quarter. So we'll start with the MP. MP stands for multi-process, obviously, which is a huge relief as opposed to sort of a resource race to the CPU cycle. Now it's you won't have that luck anymore. So in terms of multi-process, we are now near production ready with some latest PRs, adding unified, for example, unified CLI configuration along with observability and some health checks. We also have a cache blend integration through the interface and support for disaggregated prefill as well. Beside that, we can notice that we have the L2 backend support through Nixel protocol. We also have the MP operator, Kubernetes operator, with the LMCache engine CRD. And then now that the MP is done, let me just talk a bit about the northbound. So northbound is anything that is related to the vllm side of things, the inference, the attention part of the LLM. So one part of the PRs that we have, most important one is we have actually a support for more attention backends like FlashInfer or Triton attention, and that is due to some new GPU QB cache formats, and that would also allow in the future to support more layouts, which is great. We have also some stability fixes as well. In terms of southbound, we're actually moving to a more low-level kind of languages when writing the connectors, talking about more Rust and C++ based languages, and that would actually help to sort of privilege a higher throughput as opposed to Python. And the advantage here with the native self-bound protocol is that it will be easier to communicate with the Python side while using those low level languages. And that's the best of both worlds, because there's still some Python left, obviously, in inference. But in terms of backend and connectors, we will try to sort of prioritize higher throughputs through using these low-level languages. And I will end with CI/CD, some housekeeping, because we've noticed that there's been some flakiness that have been reported. So in order to address this issue, there was an overhaul, and that's mostly a major refactoring to improve the overall developer experience. So that's more or less what we have. Those are the PRs, and as you can see, like, we have a lot of contributors, and we welcome new contributors to join us anytime, because this is how the community would thrive. So this is more or less the update for now. Looking forward to share more in future for sure. That's about it, Mo. So I guess we're ready to switch to the recording.
Yes, thank you. Nick, are you still there? Do you still have it on deck?
Yes, give me a second and I'll launch it.
Wonderful.
Here we go.
Hello everyone, I'm Baolong from Tencent. Today I will talk about LMCache P2p CPU memory sharing. This work is a collaboration between LMCache Lab and Tencent and Tensor Mesh. We will discuss how to break cache silos in VM and S3 deployments. Instead of isolated instances, we introduce controller-led P2P read sharing. By the end of this talk, you will understand how to reuse KV-cache across nodes to improve his rate and TTFT. Let's look at the problem. In a typical production setup, you may have multiple VM instances with individual LMCache local CPU backend behind a proxy or named load balancer. Each LMCache manages its own KV-cache locally. This creates cache silos. For example, if you have two instances with 10 GB of cache RAM for each one, your total capacity is 20 GB, but a single request can only access the local 10 GB. If a new request hits the left instance first, it computes the KV-cache and stores it to the local CPU backend. If the same request or same prefix request later hits the right instance, it must recompute. This leads to duplicated compute and lower reuse rates. Also, RAM contention on the same host limits performance. A common solution is remote shared KV-cache using distributed file system or Redis or any other remote sharing store. The benefits are clear, persistence and scalability. However, there are trade-offs. You introduce a new stateful service to operate. More importantly, transfer latency is often bottlenecked by the TCP stack. While RDMA can solve this, but it requires full end-to-end support, includes NICs, switches, and software. Most generic remote stores, like standard Redis, usually expose TCP endpoints, not RDMA. LMCache P2P acts as a high-performance supplement to bypass those bottlenecks when hardware allows. So, what is P2P read sharing? It is a lightweight layer sitting on the top of the local CPU backend. It does not replace local cache, but supplement it. The key concept is simple. We share KV trunks across active peers without internal databases. The capacity is limited by the total cluster RAM. This means memory resources scale organically with the number of active inference instances. If you add a node, you add capacity. This significantly reduces code stats for popular content. The P2p read sharing architecture has two main components. First is the controller. Think of it as the brain of the cluster. It stores metadata. Which instance has which KV trunk? It orchestrates lookups, but never touches the actual data payload. Second is the Nixle transfer path. This is the data plane. It is optimized for reading KV cache tensors directly between nodes. By separating metadata control and data transfer, we avoid bottlenecks at the controller. Let's look at the quick setup. Step 1. Start the controller. You just define the host and port. It listens for KV cache admit event, heartbeat request, and P2p lookup request. Step 2. Launch VM instances. You need to point them to the config file and set the KV connector to LMCache connector v1. While RDMA network interface cards give the best performance. This setup also works over standard TCP/IP2 and ensure your firewall allows traffic on the specific ports. The detailed config content is posted to the LMCache document website. If you want to get the full LMCache config, you can open this link. We run a proof of concept benchmark using Llama model on a long-QA workload. We use 50 contexts with 10,000 tokens for each request, totaling about 62 GB of unique KV cache. In the test, instance 1 is cold, while instance 2 already has the data. The results are impressive. TTFT reduced by 4 times. The total runtime reduced by 5 times. This confirms that for use-rich scenarios, P2p sharing is highly effective. Real-world gains will depend on your specific traffic patterns. Next, I'd like to introduce the recent work we did. But first and foremost, a big thanks to LMCache Lab for creating the great feature of P2p read sharing. It helps us extend and improve it. Before the recent optimization, LMCache's controller and P2p backend had many issues that prevented stable production use. The first problem was complex controller structure. It used tuples and disks to maintain a flag structure with unclear hierarchy. This affected code readability and increased debugging difficulty. The second problem was easily broken heartbeat communication. The push mode easily lost heartbeat signals, and for the detection was inaccurate. This impacted system reliability and created risk of stale data. The third problem was thread-safe issues. Multi-threaded access lacked effective protection. The race conditions could correct data. This was unsafe for production workloads. The fourth problem was insufficient test coverage. There was no multi-process stress testing, making it impossible to validate performance under real production loads, and bottlenecks were unknown. The fifth problem was misconfiguration management. Configuration values were hard-coded, lacking flexibility for different deployment scenarios. Code changes were required to adjust parameters. The sixth problem was weak monitoring capabilities. There was no metric system in place to observe internal state. The system was blind to performance and health states. making issues debugging very difficult. These issues made P2p controller unsuitable for production environments, requiring a major refactor. The first thing we did is refactor the structure of metadata layout in controller. Choosing the right metadata structure is critical. We compared 3 options. Solution 0 is flag index. It offers the fastest O1 lookups, but is terrible for the deregister worker and full sync. Since seek and remove all KV-cache metadata from a large map is too slow. Solution 1. Register tree. It is our choice. It uses a tree structure, while lookups are slightly slower than O1. It reduces memory usage by 3 times and makes deregistration 4,000 times faster. This robustness is key for operations. Solution 2. Hybrid. It combines a tree with a reserve index. It fits lookup performance, but double memory usage and slow down the reporting. Why did we pick up register tree solution? Because operational stability is more important than microsecond level lookup gains. Look at the data. It is a simple test we did. Memory usage drops from 20 GB to 6 GB, allowing higher density. Worker removal takes only 8 milliseconds instead of 32 seconds, enabling instant auto-scaling. Full recovery is 23 times faster, taking just 16 milliseconds. This ensures that when things go wrong, the system recovers almost instantly. To handle high concurrency, we implemented a layered locking strategy. At the top, we have standard read-write logs for the register tree and instance node to protect structural changes. At the bottom, for the worker node, we use a custom fast log. This allows non-blocking KV admit evict operations. To design avoids expensive system calls and context switches during high-frequency KV metadata access. It ensures that changes to one worker do not block reads from another, maximizing parallelism. Well, we use heartbeat and full sync to achieve fault tolerance. First, we have heartbeat every 10 seconds. Workers send a heartbeat. If 30 seconds pass without a signal, the controller automatically deregisters the dead node. And worker can also get and run heartbeat command from the controller heartbeat response. Something like enter freeze mode command or full sync command. Second is full sync. If the controller itself restarts, it turns workers enter a freeze mode. During this time, workers pause updates and only use local CPU hot cache for reading. The controller rebuilds the global state from all workers. Once consistent in this freeze mode and normal operation resume, we choose this rather than a write-ahead log because metadata is transient and in-memory reconstruction is faster and simpler. Next, let me introduce the controller benchmark stress testing tool. We adopted the strategy pattern to design this testing tool. You can start the test with this command. Parameters include monitor ports, 50 instances, 1 worker per instance, 1 million keys per worker. Batch size is 100. Operation rates 60-second test duration and 2 client processes. The operation mix is admit at 35%, evict at 29%, heartbeat at 1%, and P2p lookup at 35%. What this test does? It launches 2 test client processes, each simulating 50 instances. with 1 worker per instance and 1 million keys per worker. When sending admit, evict, and P2p lookup requests, they are grouped into batches of 100 as one request. This benchmark can run on a MacBook and validates that the controller can handle production workloads with a good throughput and low latency. Now, let me introduce the KV-Cache verification tool. This tool ensures data consistency and integrity. In VM inference services, KV-Cache is a critical component in transformer architecture for improving inference efficiency. As model size and user inputs continue to grow, managing and verifying KV-Cache becomes increasingly important. This tool provides a self-certification means when end-to-end security issues occurred in production. The verification was as follows. Locate the VM past KV-Cache position through slot mapping. Retrieve the corresponding date to calculate checksum, and manually compare them to increase confidence. The verification workflow has 5 steps. Step 1. Enable the slot mapping recording switch. Step 2. Send the first inference request, which is a cache miss. KV-Cache is stored to MCache from the GPU KV-Cache corresponding to the given slot mapping. Obtain the slot mapping from logs. Step 3. Send the second inference request, which is a cache hit. KV-Cache is retrieved from MCache and transferred to the GPU KV-Cache at a different slot mapping. Step 4. Get the checksums from both requests KV-Cache from GPU. Step 5. Compare the KV-Cache checksums of the first and second request slot mapping. If they match, MCache storage and retrieve are working correctly. For slot mapping specification, we implemented internal compression, compressing continuous indices into start and format, greatly improve usability. Next, let me introduce an important new feature, standalone mode. Traditional MCache has been tightly integrated with VM, SSD, and other inference engines, requiring GPU resources and complex dependencies. While this works well in production environments, it creates challenge for several scenarios. First, test and development environments without GPU access. Second, pure CPU deployments in resource-constrained scenarios, such as P2p mode as pure external storage. Third, distributed hedge scenarios requiring lightweight nodes. Our solution is MCache standalone. It allows you to run MCacheEng as an independent service without VM or GPU dependencies. The implementation approach is use standalone starter, minimize simulation of VM and VM v1 adapter, while maintaining full functional parity at the MCacheEng level. The benefits are greatly reduce MCache startup time and significantly improve development and debugging efficiency. Use cases include, first, validating P2p mode by testing controller plus MCache standalone without GPU. Second, P2p as pure external storage without GPU or VM. Third, validating DeepSeek v3.2 DSA features. Fourth, validating MCache backend or remote connector extensions. Fifth, validating MCache internal APIs. Sixth, validating MCache lookup implementations, eviction policy, runtime plugin, GPU connector, matrix, and most other LMCache internal features. Now, let's discuss reliability improvements. It's about timeout and retry mechanism. P2p communication is a core mechanism for data sharing between nodes. But before this upgrade, the P2p backend implementation had a critical weakness: lack of timeout control and error recovery capabilities. When network jitter, node failures, or load spikes occurred, communication could block indefinitely, causing the entire system to stuck. This improvement completely changed this situation. We introduced complete timeout handling, auto-reconnect, and error recovery mechanism for the MCache P2p backend, transforming P2p communication from an unstable connection to a high reliability channel. Let's look at the before and after comparison. In short, the system has been upgraded from being prone to stopping and falling to being able to manage problem and changes on its own. This makes it much more stable and reliable. Next, let's discuss observability improvements. The controller matrix system. MCache controller is the central management node responsible for coordinating all MCache workers. It manages the distribution of KV cache across all MCache workers. But before this upgrade, the controller was like a black box. We could only see inputs and outputs, but knew very little about internal running state, performance bottlenecks, and resource usage. There were three core pain points. First, difficult failure diagnosis. When system issue occurred, we didn't know where the problem was. Second, missing performance analysis. Could not identify performance bottlenecks and optimization points. Third, time-consuming debugging. Each issue required intensive logging to analyze. Therefore, we introduced a metric system for MCache controller, making every request and every resource state transparent and visible. Key metrics include active request. It monitors concurrent requests being processed. KV pool key count. It tracks the number of keys in each KV pool. Socket error count. It counts network or sockets errors for troubleshooting. We mainly use llama functions to dynamically add metrics, making it very easy and simple to add new metrics. The format supports Prometheus metrics format for easy integration with monitoring system. Finally, visibility is key for ops. We provide a controller dashboard showing instance, active workers, threads, and key metrics, and many runtime internal states. Now, let's look at the production-ready features of P2p backend. Completed optimizations include 6 aspects. First, architecture stability, register tree refactor with fault recovery support. Second, thread safety, fine-grained locking protection to avoid thread safety issues. Third, heartbeat reliability, heartbeat timeout detection to identify and remove lost workers. Fourth, configuration management, config file support for flexible deployment. Fifth, monitoring capabilities, build monitoring system supporting Prometheus format metric scrapping. 6. Test coverage, supports benchmark validation for controller throughput and latency. Production environment advantage include: first, zero extra dependencies, no additional infrastructure needed. Second, gradual deployment, can start small and gradually expand worker nodes. Third, fault isolation. P2P node failures don't affect core functionality. Fourth, predictable performance. Local RAIDs prioritized. P2P RAIDs use unique so high performance transfer. Fifth, simple maintenance. Clear architecture makes issue location easy. Although we have completed many optimizations, there are still several directions that need continued improvement. First, more test cases. Increase boundary condition testing. Cover edge cases and failure scenarios. Improve overall test coverage. Second, performance optimization. Further reduce log contention. Implement fine-grained timeout and retry. Add fast fill mechanisms. Third, monitoring enhancements. Add more performance metrics. Improve observability. Better dashboards and alerts. Fourth, fault tolerance. Better node failure recovery. Reduce freeze time. Unified communication layer timeout and retry infrastructure. Fifth, P2P RAID extension. Currently, only supports RAID sharing. In future, we can extend to RAID sharing, enable full P2P cache synchronization. We welcome community contributions and feedback. Please join us on GitHub to shape the future of MCache P2P. Finally, let me do a summarization. MCache P2P controller has evolved from an experimental feature to an almost production-ready component through this batch of refactoring and optimization. These optimizations enable P2P backend to serve as an effective supplement to local CPU backend, achieving RAID sharing while maintaining high performance, laying a solid foundation for production deployment. The core value is no new hardware needed. Pure software technology enables cache sharing, expands cache space, and improves hit rate. This project is a collaboration between Tencent, MCache Live, and Tensor Mesh, and some contributors from our activity community. If you are interested in MCache P2P, welcome to take a trial and also welcome to contribute code or issues. Thank you for listening.
All right, thanks to everyone for hanging on. So Mao couldn't be here live today because time zones are hard, but we have folks on the call available to answer any questions that may have come up during that presentation. Or if there's just anything you wanted to chat about, feel free to unmute yourself and chime in, or you can put your questions in the chat and we'll read them out for you to make sure they get answered. So any questions from anyone on the call? Specifically, how is the GPU able to write directly to NVMe without ODirect, given that previously the CPU RAM backend acted as an intermediate buffer? What mechanism or buffering layer handles this transfer now?
Hey, Himanshu, I can answer this question. So basically, when you have multiple tiers of storage enabled, the policy is always write through, which means that even if your CPU is turned off, then you're still gonna write through the CPU as you mentioned. The mechanism or buffering layer is exactly the same as if the CPU RAM is turned on. It's just that when the CPU RAM is turned off, you're unable to retrieve your KV cache from the DRAM layer.
All right, that makes sense. Any other questions or comments? Oh, they're posting another one. Okay, another one from Himanshu. I noticed that LMCacheEngineBuilder.destroy engine name cleans up the LMCache backend when used programmatically. Does the same cleanup occur automatically when using vllm serve in a server client setup?
Yeah, great question. So LMCache Engine Builder is mainly used when you're, for example, writing batched inference inside of a standalone script. So when VLM is doing online inference, for example, or when LMCache is started within the life cycle of VLM, then when VLM dies, by nature of like how the OS cleans up processes, then LMCache will also be cleaned up automatically. So you don't have to call LMCacheEngineBuilder.destroy.
Okay, Himanshu has some more. Recently, we observed that NVIDIA RTX 4000 Ada GPUs enter an error state after loading the model a second time when tensor parallel size 2. After that, the system only works again after restarting the workstation. Could this be related to LMCache resources not being properly destroyed or cleaned up between model loads?
That is, so I think your intuition is right that if loading twice fails the model load on the second time, you probably have residual GPU memory that's not being cleaned up. As far as my personal experience goes, LMCache will not have an issue like this. And even let's say LMCache does have an issue like this, the space that LMCache itself actually allocates on the GPU is very small. It's less than like half a gigabyte normally. So I think your intuition is right, but you can send the error logs in the questions channel if you want. It's probably not LMCache.
Thank you for your questions. Himanshu, is there anything else you wanted to ask? Or does that cover it? Is it possible to ask a VLM production stack question?
We have Kosseila on the call, I think. Kosseila, are you still online?
Yeah.
Hi.
I'm more like the cloud related guy of production stack, but the person could always shoot.
All right, Himanshu, you can give it a try, and then if we can't answer it, you can ask him the channel.
So the VLM plus LMCache production stack currently does not natively support KV cache offloading directly to local storage. Is there a specific architectural or performance reason for this limitation? For example, is it due to latency constraints, I/O bandwidth concerns, or KV cache access patterns during inference?
Kosseila, am I wrong? But doesn't
This
production?
is more on the LMCache question, to be honest.
Okay, I think the question is whether or not like the Helm setup in production stack is able to configure disk storage. Is that the question? Because if I recall correctly, that is available. Yeah, disk storage. So I guess I can answer the second half independent of production stack is, yeah, any L2 backend, whether writing to like NVMe or a remote database will be slightly slower, but there is the async loading mode in LMCache. So you can pipeline that with the computation of other requests. But I think production stack definitely does support NVMe. So.
He can always ask the question in the channel too, because we'd have Ray to answer eventually. But yeah, like in the chart and the production stack, you have a couple of configuration. LMCache, the cache server, and also the local and also remote are also configurable in the chart. But yeah, feel free to ask the question in the production stack channel and the VLM.
Himanshu followed up because what I did, I created a PVC out of PV, then changed the structure to accept the mount point through PVC. By default, it offloads to host, which is workspace true, but after PVC, it offloads to current mount point that I provided, the correct mount point that I provided.
Sorry, what's the question here, Himanshu? I think if this is like a debug session, we can probably move this offline to the channel.
Yeah. Well, we can even get Ray to answer the question. Yeah.
Okay.
Yeah,
this is
so let's take
more
this to
kind
the
of
questions.
issue.
It's the questions channel, right? That's where we want this to go. Awesome. Thank you so much for your questions, Himanshu. We still have some time left on the call. Is there anyone else that wants to ask a question or discuss anything? All right, I think that brings us to the end then. If we're all done, thank you so much to everyone for joining. We'll share this recording in the office hour channel, and we'll get you a link to the other things that were shared, like the project updates and the recording of Mao's talk. Is there anything else you wanted to add, Nick?
No, thank you very much.
Great. Thanks, everybody. Have a great day.
Great. Thank you.
Thanks, everyone. Bye.
Bye-bye.